Lab 1 on charged tapes. So to begin, the purpose of this lab was to determine how much excess charge is on a piece of charged clear tape using a computational model. To calculate the magnitude of this charge on the tape, we are going to apply Newton's second law of motion and Coulomb's law, which will give us the electric force between two charged particles. So in this procedure to generate electric charge, we first stuck two pieces of clear Scotch tape together, measured the length of one piece, rubbed the tapes up and down, and then pulled them apart. We draped one piece over two books. This will be the bottom tape, and then we held the other out we held it out straight directly above the bottom tape. Then we slowly lowered the upper tape over the bottom tape until the bottom tape that was draped between the two books began to levitate. We measured the separation distance d between the two tape pieces when the bottom tape began to levitate. Then we will predict the magnitude of the excess charge in the tape using the glow script model that will be shown later, which we'll calculate using the momentum principle and Coulomb's law. So just an expected result, the magnitude of this charge is expected to be between 1.6 times 10 to the minus 19 coulombs, which is the charge of one proton, and between 6.02 times 10 to the 23rd multiplied by the charge of one proton equals 1 times 10 to the 5th coulombs. The second number is the amount of charge in 1 mole of protons, so we expect it to be between 1 proton and 1 mole of protons. So then these calculations show how we're going to calculate the magnitude of charge. The system is the bottom tape, and the surroundings include the upper tape, the Earth. We're essentially trying to find the force of the top tape on the bottom tape to see how this tape manages to levitate and overcome the force of gravity. So using the momentum principle, we're able to set the gravitational force equal and opposite to the electric force. They have the same magnitude but point in opposite directions. Then using the force of gravity for objects close to the Earth, we're able to find the gravitational force to be 1.225 newtons. And then just a side note, the charge here, the mass of the tape is shown in grams on this calculation, but it's actually in kilograms, and that just is that is accounted for in the glow script model. But then knowing that opposite charges attract, we can assume that the charges are equal in magnitude and opposite direction, the gravitational force and the electric force, and then as well as the two individual charges of the two tapes. And so then we're able to find the magnitude of the charge using the value that we found for the electric force on the U tape, which we found to be 1.225 newtons. And then here's a picture of what our procedure looks like. Here you can see the separation distance measured between the two tapes, and this is our little video. Skip ahead. But yeah, here we're holding the tapes over and it begins to levitate due to the electric charge. So here's a look at the glow script code. We've got constants and initial conditions. We have the K constant, the charge of a proton, which I don't think is actually used in the code here. And then the gravitational constant, the distance between the tape pieces, and the mass of the tape, which here it's correctly shown in kilograms. And then calculations. On the left, I have where I calculated the gravitational force and the electric force, and then Q. And then on the right, I have the R vectors, where I calculated the E fields so that we could show the force vectors and the E field vectors in glow script. And so here's that shown. The big red arrows are both showing the E field, and then the blue dot in the middle is the bottom tape. We're assuming it's a point charge and we're assuming it's negatively charged. And then the top circle is red. We're assuming that this one is positively charged. We just assign these charges arbitrarily to determine the E field. And then the orange arrow pointing up is the electric force, and the yellow arrow pointing down is the gravitational force. And the magnitude of charge on one piece of tape was calculated to be 1.75 times 10 to the minus 7th coulombs, which falls within our expected range, so this is a success. So some assumptions that we made using this model were that we ignored air resistance on the tapes, we just accounted for gravitational force. We treated the long tapes as point charges, with all the charge concentrated at the center of the tape, and we assumed that each tape had the same magnitude of charge evenly distributed. Some sources of error could have been if the charge was distributed to the hands or the environment and not actually all remaining on the tape, or the charges were not equal in magnitude. So some questions to think about: what if electrons had positive charge and protons were negative? Our observations in this experiment would remain the same because the tapes are still oppositely charged and opposites attract. Um, our electric field would just point in the opposite direction if, yeah, the charges were flipped. And then why is it important to handle the charge tapes as little as possible? This is just so that charge is not lost, so that we can stick as close to our assumed conditions of the tape, of the charge evenly distributed throughout the tape. And that's all. Thank you.